Okay, so our next speaker is Feng Lin from University of Warwick, who's going to speak on Monte Carlo estimation of the solution of fractional PDEs.
Hi, this is my today's topic, Monte Carlo estimation. And we know that the research of fractional partial differential equation is very popular because its application in natural science and lots of numerical method is developed to solve FPDEs, and lots of them are deterministic algorithm, for example, lattice approximation and finite element method. Only a few is probabilistic method, for example, continual time random walk approximation and exact probabilistic representation. And today I'm talking about the Monte Carlo estimation of the probabilistic representation and estimate the error, upper bound of the error between estimator and the solution, and also estimate the fluctuation via central limit theorem and construct the confidence interval. Okay, now let's see the problem. Denote the infinity RD with a continuous function and vanish at infinity. Now let G be such function, and we consider this FD2W03. Here, AX is a generator of a Feller semigroup acting on X, and the operator D is generalized differential operator of capital type of order less than 1, acting on the time variable T. Now let's see the operator of capital type. It's defined by this. Given a Levy-Marigneau satisfying this, the operator D is defined by this formula. The solution U of problem 1 exists and is given by other literature. U has stochastic representation. It's the expectation of phi x at stopping time t and the integral of g. Here, capital X is a stochastic process generated by AX, and for the stopping time t, first we define process Y with decreasing stochastic process generated by D, and stopping time t is passage time of Y crossing A. Okay, that's the solution U. We need some additional assumption. We assume that Y is decreasing of a stable Levy process. And we also assume that capital X is the process is isotropic beta stable. So this means the coordinates of X1 has the same beta stable distribution. Okay, this would make our proof easier. Now let's see the Monte Carlo estimator. Solution 2 has Monte Carlo estimator. U and H is the average of this. For the integral, I use Euler scheme. Here, H is the step length. Okay, according our additional assumption, the stopping time capital T is analytically accessible because it's a decreasing stable process passing the level. So we know the distribution of that stopping time, and so we can sample it. Then we sample the isotropic beta stable process at the stopping time T. And finally, we can simulate the estimator. Okay, now let's see our result. First, if the forcing term G is 0, so when G is 0, it's only the solution U is the expectation of phi x. And the estimator now is average of this. Clear that this estimator is unbiased. Here is our result. 1, for a continuous function phi un converge to U almost surely. Okay, this is strong law of large number. And theorem 2, if phi x satisfies this gross order, then the central limit theorem holds. This in fact is standard central limit theorem, and so this holds only. We only need to show that the second moment of phi x is finite. Is finite, and theorem 3, if phi x satisfies this, then we have upper bound of this error. This is a variant version of Berry-Esseen bound. Okay, as we mentioned, the estimator is unbiased. So the idea to prove this theorem is straight. Theorem 1, because of strong law of large number. Theorem 2 is standard central limit theorem. And theorem 3 is Berry-Esseen bound. Okay, to prove second moment is finite or third moment is finite, in fact, we can have this proposition assume that the stochastic process X is a beta stable process. Then the tail of capital X at a stopping time t has this order. So okay, with this tail, we only need to control the function phi. So it's only we only need that it does not grow too fast. Then it have finite second moment or finite third moment. That's it. For the proof of this proposition, since capital X is beta stable, so we can scale it. And the stopping time t, we know that the distribution of it. So let's provide some ideas to prove this proposition. Okay, that's basically the idea about when G is 0. Now let's see, when the forcing term G is not 0, the estimator is biased. Here we need an additional assumption. We assume that G satisfies this holder condition. I said there where
you have like a normal x minus 1 and then down. Oh, I see.
Okay, here is our result. Assume phi x has this order, then claim that the Monte Carlo estimator convert to the solution in L2. And also we have central limit theorem with a bias correction. Okay, let Hn be this. Then we define z tx such that u is the expectation of z. Then we have the central limit theorem. Okay, here is some ideas about this proof. We define YH be the approximation of Z. We can show that the L1 error between Z and YH has this kind of upper bound, and with some similar proposition, we can show that the Monte Carlo estimator U and H and U, it converges in L2. For the central limit theorem, we apply the triangular array method to prove this. Okay, that's basically the ideas of how to prove this theorem. Now let's see the confidence interval. So we can use central limit theorem in L2 to get asymptotic confidence interval. Okay, the central limit theorem can be written using convergence in distribution. So once we have the upper bound of variance z, and we can get asymptotic confidence interval about the upper bound of variance z. Well, it's similar to using this kind of proposition. Okay, that's the confidence interval. And here is some example of the confidence interval. Here we can see that we got we set phi x be 1 and g be the square root of x. And this is a asymptotic confidence interval at level 95. Okay, that's basically tell us the fluctuation of the Monte Carlo estimator. Here is some reference, and okay, thank you for listening.
Yeah, sorry.
You mean psi? Yes. In our result, I using it. I think we can, but we cannot write the Berry-Esseen bound in this form because, okay, this form it relies on the third derivative. But so if we don't request it has third derivative, we need to prove it in another way. I think I can do it because basically so if we have third moment is finite, then the Berry-Esseen bound exists, right? Okay, that's the key point of the Berry-Esseen bounds. I believe the C3 is not necessary.
Okay, any more questions?
Yeah.
Yeah, so one of the running assumptions was that this, one of the processes was a stable coordinate space going down, right?
Yeah.
And I think the thing you mentioned was that the important part was that you can simulate, right?
Yes.
I mean, the skipping time. If you had another subordinator to possibly extend some of these things, I mean, another subordinator for which you know how to simulate heating time. For example, tempered stable subordinator.
I think, well, the stable property of this Y is important. Well, it's in the proof of this proposition. This proposition. Okay. So X wait a minute. Okay, let's see this equation 2.4. That's it. Capital X at stopping time t. Okay, we write it in this form. And then this is how I try to prove the tail of capital X at the stopping time t, and this relies on the stable property of the stopping time t.
But okay, as far as I understand this proposition, the purpose was to bound the tails and get like nice simple conditions to ensure that you have as many moments as you want.
Yeah.
Like second, third moment. But let's imagine you have just that additional assumption. You have several moments, as many moments you have. Could you try and do this with different subordinates?
Maybe. Yeah, I think I can. But for this part, to prove the tail of this, it's different from here.
Okay, Zizhwab.
Yes.
Can you consider the equation in bounded domain? Question one. Question two, can you consider equation of your equation is linear? Can you add potential there? Single order there to the equation.
Okay, you mean the
by some bounded domain.
that would be more difficult, I think.
Okay, so you answered here.
Uh,
I just wondered whether you have done that.
Not yet. Well, my argument mainly based on the solution is given. So if you add more terms, the solution might be different, I think.
Yeah.
And so the approximation, the Monte Carlo estimator would be different. And
So you didn't. And the second question, can you add 0 over the terms? Right? Something would be also possible or not?
I think it's possible.
What do you mean by 0 over the terms? You multiply by U. That would be 0 over the terms.
Okay, thanks very much. Shall we thank all the speakers from this afternoon again?